A faint, repeating whisper drifts through the void from a failed star. This is the sound of a cosmic mystery unfolding around brown dwarfs, celestial objects caught between planets and stars. These enigmatic bodies are broadcasting signals that defy all our expectations. By the end of this journey, you will know the 25 most unexplained transmissions that are rewriting astronomy. We will explore signals with mathematical patterns and bursts of energy that vanish without a trace. What do you believe is waiting for us in the dark? The first signal arrives from a place of profound cold and quiet. Y0855-0714 is one of the coldest brown dwarfs ever discovered, a cosmic failure drifting in the void with a temperature barely above that of a winter day on Earth. From this frozen, nearly starless world, astronomers detected a faint but persistent whisper. It was not a random blast of static. This was a repeating radio signal, a rhythmic pulse that appeared and faded with a strange, almost deliberate regularity. Its most baffling feature was its frequency modulation. The signal's pitch wavered in a complex pattern, rising and falling in a way that does not match any known type of stellar flare or magnetic storm. Normal star activity creates chaotic bursts of energy, not this delicate, repeating cadence. One compelling theory points to a natural yet incredible atmospheric phenomenon. Imagine colossal weather systems in its alien atmosphere, storms larger than Jupiter generating lightning of unimaginable power. These discharges could, in theory, create structured radio waves. But the precision of the modulation gives scientists pause. Could atmospheric turbulence alone produce such a clean, repeating pattern? Or does this whisper from the cold hint at processes we have not yet begun to understand, something stirring within the deep, dark atmospheres of these failed stars? The strange regularity from that frozen world was soon followed by a sound of pure violence. From the Luhman 16 binary system, the closest brown dwarfs to our own sun, a single, shattering burst of energy erupted into the silence. This was not a gentle, repeating whisper. It was a scream, a blast of radio waves so powerful it briefly outshone every other natural source in its region of the sky. And then, just as suddenly as it arrived, it was gone. That single, brilliant flash lasted for less than a minute, a cosmic event witnessed only once and never again. The sheer power of the burst ignited a fierce debate that continues to this day. One school of thought points to a magnetic cataclysm. Brown dwarfs possess incredibly powerful magnetic fields, and a star spot, a dark region on its surface, could have reconfigured in an instant. This magnetic reconnection would release a flare of epic proportions, a stellar tantrum of raw energy, but the sheer, focused intensity of the signal gives other researchers pause. It was so clean, so potent. Could a natural flare truly concentrate that much energy into such a brief, singular event? The alternative is both thrilling and unsettling. Could it have been a transient, artificial broadcast, a single, powerful message or beacon that swept past our detectors, a call we heard for mere seconds and were never able to find again? We are left with a profound and haunting question. Did we intercept a natural, if terrifyingly powerful, stellar event, or did we, for 50 fleeting seconds, listen to a signal not meant for us? The silence after that brilliant scream was broken by a new kind of pattern, one that seemed to carry a whisper of intelligence. From the general vicinity of the Teegarden star system, a series of irregular, pulsed signals began to arrive. These were not the rhythmic beats from the frozen brown dwarf, nor were they a single, shattering blast. They came in clusters, a staccato of radio pulses that seemed to dance to a complex, almost coded rhythm. The timing between pulses was erratic, yet within that chaos, researchers found a strange mathematical structure, a pattern of intervals that did not fit the profile of any known pulsar or flaring star. It was as if the void itself was tapping out a message in a language we could not yet decipher. The most immediate and exciting possibility was that we were listening to a technosignature, an artificial broadcast from another civilization. The pulsed nature and complex coding-like structure are exactly what scientists predict an intentional signal might look like, designed to stand out against the background noise of the cosmos. Yet the universe is a master of mimicry. A compelling natural explanation points to auroral emissions on a colossal scale. Picture the magnetic field of a brown dwarf, a vast, invisible web stretching into space. As charged particles rain down upon its atmosphere, they could ignite a celestial light show, a radio aurora that flickers and pulses in unpredictable ways. The complex patterns might simply be the sound of a world's magnetic field twisting under unimaginable stresses. So we are left to wonder, are these pulses the static crackle of an alien aurora, or the first faint notes of a symphony composed by minds not our own? That rhythmic, coded tapping was soon joined by a sound more akin to a cosmic metronome. Deep within the constellation Leo, the brown dwarf known as 2-mass J1047+21 began to broadcast a series of pulses of breathtaking precision. These were not the chaotic clusters from before, but a steady, reliable beat, a rhythmic ticking so consistent it could rival the most accurate clocks on Earth. The pulses arrived with a regularity that was almost musical, a perfect tempo held for hours on end. This behavior is the hallmark of a pulsar, a rapidly spinning neutron star that sweeps beams of radiation across the cosmos like a lighthouse. But 2-mass J1047+21 is no pulsar. It lacks the unimaginable density, the collapsed stellar core that powers those cosmic beacons. This is a failed star, a gaseous body that should not be capable of such a disciplined, unwavering performance. Astronomers are now faced with a profound puzzle. What internal engine could possibly drive these perfect pulsations? One leading theory delves into the star's deep, churning interior. Vast global oscillations may be rippling through its atmosphere, like the resonant ringing of a colossal bell. These vibrations could periodically heat the upper layers, causing them to brighten in a regular, predictable rhythm. Another possibility involves a magnetic cage. The brown dwarf's powerful magnetic field might be channeling charged particles toward its poles, creating hotspots that rotate in and out of view, generating the pulse. Yet the sheer stability of the signal challenges both ideas. How does a turbulent, storm-racked world maintain such perfect time? The beat goes on, a hypnotic rhythm from an object that defies its own nature, forcing us to question what truly stirs within the hearts of these dark stars. The steady rhythm from Leo was shattered by a storm of raw power. SIMP J0136+09 is a rogue brown dwarf, a cosmic nomad drifting alone through the dark between stars, untethered from any solar system. From this isolated wanderer, astronomers witnessed not a single pulse or a solitary scream, but a veritable hurricane of radio flares. These were not isolated events. They erupted in a furious cluster, a series of intense, overlapping bursts that created a cacophony of energy, each one releasing more power than our sun might in a significant solar flare. The sheer concentration of such violent activity in such a short period was unprecedented. It was as if the object had suddenly awakened in a fit of rage. What could possibly stir a solitary, frozen world to such a frenzy? The most compelling clue lies not in the brown dwarf itself, but in the empty space around it. Scientists suspect it may not be alone. The leading theory proposes an unseen planetary companion, a hidden world locked in a tight, gravitational dance with its failed star. As this hypothetical planet swings close on its elliptical orbit, its gravity could squeeze and distort the brown dwarf's interior, much like the moon tugs on Earth's oceans. This gravitational kneading might be twisting the brown dwarf's powerful magnetic fields, building up stress until it catastrophically releases its energy as a storm of radio fire. It is a cosmic domino effect where an invisible dance partner triggers a visible eruption. Yet this remains only a hypothesis, a ghost story told to explain the fireworks. Despite our best efforts, no planet has been directly observed there. We are left with the spectacle of the storm and a profound question echoing in the void. Is this the signature of a hidden world we cannot see? Or is it the sound of a lone brown dwarf convulsing in ways we have yet to comprehend? The storm of flares from that rogue nomad was a spectacle of raw chaos, but the next signal presented a puzzle of eerie control. From the dim brown dwarf CFBD J1047+10, astronomers recorded a transmission that seemed to defy the very nature of radio waves. The signal did not simply fade in and out. Instead, its frequency abruptly plummeted, not once but multiple times, as if an invisible hand was twisting a dial, systematically shifting the pitch of a cosmic broadcast into a lower register. These sudden, discrete drops were too clean, too sequential to be easily dismissed as random noise. It sounded less like a natural phenomenon and more like a deliberate adjustment. To explain this, scientists looked to the churning plasma soup of the brown dwarf's own atmosphere. Within that superheated, electrically charged gas, vast instabilities could be forming. Think of it as a celestial short circuit. A bubble of plasma might grow unstable and suddenly collapse, or a magnetic loop could snap and reconfigure. Each of these events could fundamentally alter the environment through which the radio waves travel, effectively retuning the signal to a lower frequency as it escapes. It would be like a sound wave moving from the open air into a thick, dense fog, its pitch warping as it passes through. This is a compelling, entirely natural explanation. Yet the precision of those drops gives some researchers pause. The pattern is unsettlingly reminiscent of a technique we use ourselves, frequency hopping, a method for making communications more secure and robust against interference. Is it possible we are seeing the signature of a natural plasma oscillator, a bizarre new type of stellar weather? Or does this cosmic dial twisting hint at something far more profound, a signal engineered to be clearly artificial by an intelligence that understands the language of radio itself? From the twisting dial of a controlled signal, we now encounter a cosmic echo. SIMP J0147+4642 broadcast a transmission that did not simply end. Instead, it seemed to bounce back, returning to our receivers a short time later with a faint but distinct delay. This was not the steady beat of a metronome or a chaotic burst. It was a whisper that came twice, a signal and its own ghost. Such a reverberation is almost unheard of from a deep space object, creating an immediate and profound mystery. Was this a natural sonic boom in the void, or something else entirely? One plausible explanation lies in the complex terrain of interstellar space. Imagine the signal traveling from the brown dwarf and encountering a vast, invisible wall, a cloud of ionized gas, or perhaps the outer shell of a long-dead star. This cloud could act as a mirror, reflecting the original transmission back toward us along a slightly longer path, creating that haunting delay. It would be like shouting into a canyon and hearing your own voice return a moment later. Yet, this natural echo chamber theory faces a significant challenge. The space between stars is overwhelmingly empty. For a signal to find such a perfect, discrete reflector by chance is statistically very rare. This improbability fuels a more electrifying possibility. Could the echo be a form of deliberate retransmission? A hypothetical intelligence, upon detecting its own signal being monitored, might intentionally bounce it back as a way of signaling its presence, a cosmic game of ping-pong designed to capture our attention. The echo from the void thus presents us with two vastly different realities. Do we live in a universe where chance formations create perfect cosmic echoes, or one where someone or something is listening and choosing to answer? The echoes from the void were soon joined by a sound of unexpected harmony. From the Brown Dwarf Gliese 570D, a signal arrived not as a single note but as a complex chord. It was composed of multiple harmonic frequencies, a cascade of interwoven radio waves that created a single, intricate wave pattern. This was not random noise. It was a structured emission, a natural symphony of frequencies where each tone was a precise mathematical multiple of a fundamental pitch. The universe is rarely this musically inclined by accident. This harmonious structure presents a classic scientific riddle. Is it the signature of a natural physical process, or is it a beacon engineered to be noticed? The most compelling natural explanation lies in the concept of resonance. Picture the Brown Dwarf's entire atmosphere as a single, massive musical instrument. Vast global oscillations, like the standing waves in a colossal organ pipe, could be rippling through its gaseous layers. These resonant vibrations would naturally excite specific harmonic frequencies, causing the entire world to ring like a bell, broadcasting its complex tonal signature into the cosmos. It is the sound of a world singing its own internal song. Yet, the very cleanliness of these harmonics gives other researchers pause. In our own technological endeavors, we use harmonic structures deliberately. They are a fundamental part of how we encode information in radio and television signals, a way to pack more data into a transmission and make it clearly artificial. The Gliese 570D harmonic pattern is so well defined, so mathematically pure, that it perfectly mimics what we would expect from a designed broadcast. So we are left to ponder the nature of this cosmic chord. Are we hearing the resonant hum of a giant world's atmosphere, a natural physical process on a staggering scale, or are we listening to a carefully constructed signal, a complex message from the dark, deliberately composed to stand out from the background static of the universe? The harmony is beautiful, but its origin remains one of the deepest mysteries. The cosmic symphony from Gliese 570D was a model of harmonic consistency, but our ninth signal is a study in pure unpredictability. From the Brown Dwarf HD3651b, a powerful beacon flickers into existence, only to vanish for days, weeks, or even months at a time. Its appearances are utterly random, a frustrating game of cosmic peek-a-boo that defies all attempts at long-term observation. Just when astronomers think they have locked onto its pattern, the signal winks out, leaving only silence and a trail of incomplete data. This sporadic behavior creates a monumental challenge for science. How do you model something that refuses to follow any predictable schedule? The core of the mystery lies in the turbulent, chaotic environments of these failed stars. Our current understanding of brown dwarf magnetospheres and weather is still in its infancy. We know they possess powerful magnetic fields and host storms of unimaginable scale, but the interplay between these forces is wildly complex. One compelling theory suggests that the signal is tied to a specific colossal storm system in the brown dwarf's atmosphere. Picture a hurricane larger than Earth, a swirling vortex of gas and charged particles. When this storm rotates into a position where it can interact with the global magnetic field in just the right way, it might act like a natural antenna, switching the radio beacon on. Then, as the storm continues its chaotic dance, that perfect alignment is lost and the signal is abruptly cut off. The random timing would simply reflect the inherent unpredictability of weather on a global, alien scale. Yet, this explanation is unsatisfying for some. The signal's power and clarity are difficult to reconcile with a process as messy as atmospheric turbulence. The intermittent nature itself is a profound puzzle. Is this the sound of a naturally flickering stellar environment, or could it be a form of deliberate, sporadic broadcasting, a beacon designed to be difficult to track and even harder to understand? The silence between the bursts is as telling as the signal itself, a reminder that the cosmos guards its deepest secrets with a frustrating yet captivating randomness. While one brown dwarf can present a profound riddle, two dancing together create a symphony of coordinated mystery. The Epsilon in Dye system hosts a pair of these failed stars, Ba and Bb, locked in a mutual gravitational embrace. What astronomers witnessed here was not two separate, random broadcasts. Instead, the emissions from one component seemed to directly trigger an immediate, responsive signal from the other. It was a cosmic duet, a call and response played out across the void. One would pulse and its partner would answer, not with a random flicker, but with a distinct and timed emission of its own. This coordinated behavior is unlike anything seen in solitary brown dwarfs. The most elegant explanation lies in the invisible architecture of their shared space. Each brown dwarf possesses a powerful, complex magnetic field. As they orbit one another, these magnetic fields could be physically linking, creating a vast bridge of magnetic force between them. When a flare erupts on one star, a surge of charged particles could travel along this magnetic highway, slamming into the atmosphere of its companion and sparking a responsive flare. It would be like one bell being struck and its vibration traveling through a connecting wire to ring a second, distant bell. This is a beautifully natural process, a demonstration of celestial physics on a grand scale. Yet the precision and immediacy of the response raise deeper questions. Could there be an even more fundamental, unknown energetic process at work, one that allows these failed stars to communicate their internal states to one another directly? Are we witnessing a natural form of synchronization where the rhythmic beating of two stellar hearts becomes one? This coordinated dance challenges our understanding of how isolated objects can become so deeply intertwined, forcing us to wonder if we are seeing mere magnetic linkage or the first evidence of a new collective cosmic behavior. The coordinated dance of the Epsilon in Dye system reveals how interconnected these worlds can be, but some signals move to a rhythm all their own. From the solitary brown dwarf SER 1845-6357, a long, slow sigh has been detected. Its radio emission does not hold a steady pitch. Instead, it drifts, sliding almost imperceptibly lower in frequency over many months, a continuous Doppler shift that paints a picture of subtle, relentless motion. This is the kind of signal change astronomers routinely see from distant stars, and it almost always points to one thing: orbital movement. The slow, persistent drift is a classic fingerprint of a Doppler shift, the same effect that makes a siren's pitch drop as a police car speeds away from you. But here, the source is a single brown dwarf. So what exactly is moving? The most tantalizing explanation is that we are not hearing from the brown dwarf alone. This cosmic soloist may have a silent partner, an undiscovered exoplanet too small and dim for our telescopes to see, could be orbiting this failed star. As the brown dwarf and its hypothetical companion swing around their common center of gravity, the brown dwarf would gently wobble. When it wobbles slightly away from us, its radio emissions are stretched, causing the frequency to drift lower. Then, as its orbit carries it back, the frequency would theoretically drift back up. We are essentially hearing the ghostly signature of an invisible world, its gravity tugging on its parent star and imprinting its presence on the very light we receive. Another compelling possibility involves a broader, more diffuse structure. Instead of a single planet, a vast disk of rocky debris and dust could be encircling the brown dwarf, a remnant of its formation. The collective gravitational pull of this entire disk, or perhaps the motion of a particularly dense clump within it, could be imparting that same slow, steady wobble. This would be a fossilized solar system in miniature, a failed star surrounded by the ruins of planets that never were. Yet the mystery deepens because we have not yet visually confirmed either a planet or a disk around this object. The signal itself is the only evidence, a spectral line that will not stand still. This leaves us with a profound and elegant puzzle. Is that slow, drifting sigh the sound of a hidden world we cannot see, a testament to how common planets truly are? Or is it the whisper of a dusty graveyard, the ghost of a system that never quite came to be? The drift continues, a slow-motion clue written in the fabric of space itself. The slow, drifting sigh from one lonely world was soon contrasted by a signal of astonishing mathematical purity. From the brown dwarf known as 2-mass J1507+1627, a series of pulses arrived that seemed almost too perfect to be natural. The intervals between each pulse were not random. They followed a distinct mathematical sequence, a repeating pattern of long and short gaps that could be charted on a graph with clean, predictable lines. This was not the chaotic rhythm of a storm or the steady beat of a resonant world. It was a structured cadence that immediately sparked a thrilling and dangerous thought. Had we finally found a signal engineered by intelligence? The pattern was so deliberate, so unlike the usual noise of the cosmos, that the possibility of a technosignature could not be easily dismissed. This is exactly the kind of ordered complexity our own civilization might broadcast to announce its presence. Yet, the universe has a way of creating order from chaos through simple physical laws. The most compelling natural explanation lies in the object's rotation and its own fiery weather. Imagine two colossal, permanent storm systems on opposite sides of the brown dwarf, vast hurricanes of superheated gas that act as brilliant hotspots. As the dwarf rotates, these hotspots spin into and out of our view, much like a lighthouse beam sweeping across a dark sea. If the storms are not perfectly symmetrical, their passing would create a pattern of alternating long and short intervals in the radio pulses we detect. The mathematical sequence would then simply be a reflection of the object's fixed rotation and the stable positions of these immense atmospheric features. It is a clockwork mechanism driven by the simple, relentless spin of a world, so we are faced with two profoundly different interpretations of the same beautiful pattern. Is the rhythm from 2-mass J1507+1627 the product of a cosmic clock, a natural pendulum swinging in the deep, or does its mathematical heart beat to the tune of a distant, unknown composer? The pattern remains, a riddle written in the silent language of time and space. The mathematical pattern from the previous brown dwarf was a tantalizing puzzle, but our 13th signal is a story of a ghost. From the direction of LHS 102BC, a faint, fleeting whisper was recorded by a single radio telescope. It was an exceptionally weak signal, barely rising above the background hiss of the cosmos, a fragile thread of data that appeared just once and then dissolved back into the eternal silence. Despite astronomers pointing the world's most sensitive instruments back at that exact spot in the sky for years, the signal never returned. It left no trace, no echo, no repeating pattern to confirm its existence. This is the profound challenge of transient astronomy. How do you study something that refuses to be seen a second time? The immediate and most likely explanation is a simple, earthly one: instrumental error. Even our most advanced technology is not perfect. A random glitch in the telescope's electronics, a burst of internal noise, or a stray cosmic ray striking the detector can all create a false signal, a digital mirage that looks real until you try to find it again. Alternatively, the ghost could have been local interference, a passing satellite, a distant airplane's radar, or even a malfunctioning microwave oven in the observatory's break room can inject a brief, artificial signal into the data stream, a human-made phantom that tricks the instruments. Yet the possibility remains that the signal was real. The universe is filled with one-off events, stellar hiccups or collisions we are fortunate to witness only once. This single, unverified whisper forces a humbling lesson upon us. In the search for cosmic truths, a single data point is a story without an ending. It is a reminder that for every mystery we solve, the void offers another that may forever remain just beyond our grasp, a fleeting shadow on the edge of perception. While some signals tease us with their patterns, others challenge us with their very structure. The 14th signal, emanating from the Ross 458AB system, arrived with a strange and distinctive spin. Its radio waves were not simply vibrating back and forth. They were twisting, corkscrewing through space in a tight, circular pattern known as anomalous circular polarization. This is not a common property of random stellar noise. It indicates a high degree of order, a coherence that suggests the waves were born in an environment of incredible magnetic organization. This specific type of polarization immediately narrows down the possible sources, creating a fascinating fork in the road of scientific interpretation. On one hand, this twisted signal could be the definitive signature of a powerful and complex magnetic engine. Brown dwarfs are known to have intense, tangled magnetic fields. If a flare or an auroral event occurs within a particularly ordered and stable part of that field, it could impart this clean, circular spin to the radio waves as they escape. It would be the natural fingerprint of a cosmic magnetic dynamo working with unexpected precision. The other possibility, however, sends a ripple of excitement through the search for extraterrestrial intelligence. A circularly polarized wave is remarkably resilient. It resists the distorting effects of interstellar space far better than an unpolarized signal. For this reason, it is a property we would deliberately engineer into a long-range interstellar beacon. A signal designed to travel vast distances and still arrive intact would likely look exactly like this. It is the difference between shouting randomly and speaking through a finely tuned megaphone. So the question hanging over Ross 458AB is one of origin. Are we witnessing the pinnacle of natural magnetic phenomena, a level of stellar order we never knew possible? Or have we intercepted a broadcast deliberately crafted for a journey across the light years, a message spun into existence not by chaos but by design? This twisting, polarized signal was followed by an explosion of pure bandwidth. The Brown Dwarf SDSS J1047+1348 did not broadcast on a single frequency. Instead, it erupted across a vast spectrum of radio waves all at once, a roaring cascade of energy that flooded the receivers of our telescopes. This was a broadband burst, a signal that rejected the idea of a single, clean note in favor of a deafening cosmic chord played on every channel simultaneously. Such a wide-ranging emission is extraordinarily rare in nature, where most stellar processes are tuned to very specific, narrow frequencies. It was as if every instrument in an orchestra began playing a different tune at the exact same moment. To create such a chaotic yet powerful event requires a source of immense and indiscriminate energy. The leading natural hypothesis points to a cataclysmic particle acceleration event. Deep within the Brown Dwarf's powerful magnetic field, a sudden instability could have occurred, perhaps a magnetic reconnection that acts like a colossal slingshot. This event would have hurled a storm of electrons and other charged particles to velocities approaching the speed of light. As these frenzied particles spiral along the magnetic field lines, they emit radiation across a huge swath of the spectrum in a single, brilliant flash. It is the sound of a star violently shaking off a part of itself, yet the sheer breadth of the burst also aligns perfectly with a more profound idea. In our own efforts to search for intelligence, we design broadband beacons for a simple, logical reason. A signal that spans many frequencies is far more likely to be detected by an unknown listener, regardless of which specific frequency their telescope happens to be monitoring. It is the communications equivalent of casting a wide net instead of a single fishing line. This broadband burst could therefore be the ultimate cosmic flare, a natural event of staggering power. Or it could be the most efficient design for a beacon ever conceived, a shout into the darkness designed not for elegance but for the highest possible chance of being heard. A whisper from the cosmos can sometimes die out before our very ears. From the brown dwarf known as 2-mass J0139+02, astronomers tracked a signal with a deeply unsettling characteristic. It was a pulse that did not vanish abruptly. Instead, it faded gradually over a series of observations, growing weaker and weaker with each passing month until it was lost entirely. This slow, deliberate dimming is highly unusual. Standard stellar flares explode and decay rapidly. They do not typically fade away over such an extended period in such a linear, controlled manner. The slow death of this pulse points toward a systemic change, a fundamental shift in the environment that created it. One compelling theory is that the brown dwarf itself was entering a new phase of its long, cool life. Its internal magnetic dynamo, the churning engine of liquid metal that generates its powerful field, could have been settling into a more stable, less active state. As the magnetic field weakened or reconfigured, the energetic processes that powered the radio pulse would have slowly starved, causing the signal to dwindle like a fire running out of fuel. It would be the sound of a stellar heartbeat slowing down for a long celestial winter. Yet another, more dynamic possibility involves an unseen celestial dance. Imagine a large, dark object, perhaps a planet or a dense cloud of debris, orbiting the brown dwarf. As this object moved along its path, it could have begun to pass directly between the source of the pulse and our line of sight. Month by month, it would have blocked more and more of the signal, creating that precise, gradual fade as it eclipsed the source, before moving fully into position and silencing it completely. This would not be a change in the star itself, but a trick of cosmic geometry, a slow celestial curtain being drawn closed. The fading pulse leaves us with a haunting ambiguity. Did we witness the internal fire of a failed star quietly burning out, or were we simply watching the shadow of a hidden companion fall across its light, a final act in a silent orbital ballet we could not see? The silence left by a fading pulse was broken by a sharp, rising tone. WISE 1541-2250 produced a sound unlike any other, a rapid chirp where the signal's frequency climbed swiftly before cutting off. This was not a slow drift or a sudden burst, but a distinct upward sweep, like the brief, high-pitched whistle of a celestial tea kettle. Such a clean frequency ramp is a rare and telling signature in the cosmos, pointing directly to a dramatic and rapid change in the environment where the signal was born. One of the most compelling astrophysical scenarios involves a violent plasma ejection. Picture a colossal flare on the brown dwarf's surface, so powerful that it hurls a blob of superheated, magnetized gas out into space at a significant fraction of light speed. As this blob of plasma races away from the star, the radio waves emitted from within it are compressed. This compression forces the waves to arrive at our telescopes at a higher and higher frequency, creating that distinctive upward chirp before the blob dissipates or moves out of range. It is the sound of a star literally throwing a part of itself into the void. Yet another, even more mind-bending possibility exists, one that pulls on the fabric of space-time itself. What if a massive, invisible object passed very close to the brown dwarf? A rogue planet, a hidden black hole, or even a dense neutron star could have swung by on a near-collision course. As this object approached, its immense gravity would have warped the space around the brown dwarf, briefly acting like a lens. This gravitational lensing would have stretched the path of the radio waves, initially lowering their frequency. Then, as the object moved away, the space would snap back, causing the frequency to rebound and rush upward in that rapid chirp. We would be hearing the echo of a ghostly mass bending the universe itself, a fleeting distortion recorded as sound. So the question remains, did we witness the explosive birth of a stellar cannonball, a natural event of raw power? Or did we intercept the acoustic shadow of a dark wanderer passing silently through the cosmic night, its presence revealed only by the way it tweaked a single note from a failed star? The chirp is a brief clue to a moment of profound and violent change, a split-second event whose cause remains suspended between two equally incredible realities. The sharp chirp of an accelerating blast gives way to a silent chemical fingerprint, J0758b presented a mystery not in its radio voice but in the very light it emitted. When astronomers analyzed its spectrum, the breakdown of its light into individual colors, they found something deeply irregular. Specific chemical signatures were either glaringly absent or shining with impossible brightness. It was as if the orchestra of its atmosphere was missing entire sections of instruments, while a single trumpet played a deafening, solitary note. These spectral lines, the unique barcodes for elements like methane or potassium, were completely out of balance, pointing to an atmosphere in a state of profound chemical chaos. This anomaly is a direct window into the alien weather raging deep within. One leading theory involves a colossal, permanent storm, a hurricane larger than any planet in our solar system. This vortex could be acting like a massive atmospheric elevator, dredging up exotic chemicals from the brown dwarf's deep, hot interior and hurling them up to the visible surface. There, they would glow with unnatural intensity before being churned back down into the abyss. Alternatively, the storm itself might be consuming certain molecules, breaking them apart in its furious winds and creating dark, missing bands in the spectrum where those chemicals should be. This is not a static world, but a dynamic chemical factory with its products and byproducts churned by global turbulence. Yet, the sheer extremity of the anomaly raises another, more speculative possibility. Could we be seeing the effects of external pollution? If a large, icy comet or a rocky planetesimal had recently collided with the brown dwarf, it would have vaporized upon impact, injecting a massive, foreign dose of new elements into the atmosphere. This cosmic contamination would temporarily overwhelm the native chemistry, brightening some spectral lines and suppressing others as the alien material mixed and dissipated. The strange light from J0758b forces us to ask a fundamental question. Are we looking at the natural, if violent, breath of a churning world? Or are we witnessing the aftermath of a cosmic accident, the scattered remains of an obliterated wanderer now staining the sky of a failed star? Sometimes, even the most reliable cosmic clocks begin to falter. Our journey brings us back to the brown dwarf 2-mass J1047+21, the source of that once perfect metronome pulse. After its initial discovery, astronomers embarked on a long-term monitoring campaign, expecting to simply confirm the beautiful, unwavering rhythm they had first recorded. Instead, they witnessed something far more intriguing and unsettling. The steady beat began to change. Over months and years, the pulse did not simply fade. Its tempo began to waver, speeding up and slowing down in subtle, unpredictable shifts. The intervals between pulses stretched and contracted in a slow, complex dance that defied their original, simple model of a rotating hotspot or a resonating bell. This evolution transformed the mystery entirely. A stable clockwork mechanism had revealed itself to be a living, breathing system, one with a hidden depth of complexity. The initial theory of a stable, rotating storm now seemed too simplistic. How could a fixed atmospheric feature produce such a fluid, changing rhythm? Scientists were forced to reconsider the star's very interior. Perhaps the global oscillations rippling through its gaseous body were not simple, standing waves. Instead, they might be interacting with each other, creating a chaotic interference pattern where different vibrational modes compete for dominance. One mode might be stronger for a few months, setting a faster tempo, before another mode takes over and slows the pulse down. It would be like listening to an orchestra where different sections of musicians keep subtly changing the piece's rhythm, creating a symphony that never repeats exactly. This internal interference points to a dynamic and turbulent inner life far more complex than we ever imagined for these cold, dark objects. Yet the changes observed were not entirely random. There were hints of longer-term cycles buried within the data, patterns that might unfold over decades. This suggests the changes are not pure chaos, but part of a grander, slower process we are only beginning to perceive. The evolving pulse of 2 mass J1047+21 is a profound lesson in cosmic patience. It tells us that the signals from these failed stars are not static snapshots. They are living narratives, stories written in the language of shifting frequencies, and we have only just begun to read the first few pages. The frustrating randomness of HD3651b's signal has pushed astrophysics into the realm of advanced simulation, where supercomputers now attempt to replicate its maddening game of cosmic hide-and-seek. Scientists have constructed intricate digital models of the Brown Dwarf, feeding in everything we know about its temperature, rotation, and probable magnetic field strength. The most promising results point not to a single cause, but a perfect storm of internal and external chaos. One leading model focuses on the concept of sporadic magnetic reconnection. Imagine the Brown Dwarf's magnetic field as a vast, tangled web of rubber bands stretched to their breaking point. In most stars, these reconnection events are localized and frequent, creating a steady crackle of small flares. The model suggests that on HD3651b, the field is so complex and unstable that stress builds up unevenly across the entire globe. The system remains locked and silent for weeks until a single critical knot in the magnetic web suddenly snaps. This triggers a domino effect, a cascading reconnection that unleashes a powerful, continent-sized flare and its accompanying radio burst. The signal screams into existence, only to vanish as the magnetic field settles into a new, temporary equilibrium, beginning the slow process of building up stress all over again. This creates the sporadic timetable, a rhythm of buildup and release that is inherently unpredictable. Another compelling digital theory introduces an external actor, a circumstellar dust cloud. The model proposes a thin, uneven ring of rocky debris and ice crystals orbiting the Brown Dwarf. As this cloud moves, dense clumps within it periodically drift between the primary emission source on the star and our line of sight. These clumps are not solid enough to block visible light, but they are perfectly capable of absorbing or scattering the specific radio frequencies we are trying to detect. In this simulation, the signal is actually firing almost continuously from a powerful storm system on the Brown Dwarf. We only hear it when a fortuitous gap in the dusty veil swings into place, giving us a fleeting, clear window to the hidden activity below. The sporadic behavior is not the signal turning on and off, but our window to it opening and closing. So the mystery of HD3651b splits into two equally fascinating digital realities. Is it a world with a magnetic personality prone to sudden, catastrophic tantrums? Or is it a steadily broadcasting beacon, its message filtered and broken by the swirling dust of its own cosmic construction site? The models run, each producing a flickering pattern that mimics the real one, yet the truth remains just out of reach, a ghost in the machine of our own creation. The brilliant, singular scream from the Luhman 16 system demanded a deeper investigation, so astronomers turned the full force of modern astronomy upon it. They meticulously combed through the data archives, searching for any other trace of that cataclysmic flash across the entire electromagnetic spectrum. Had it been accompanied by a furious spike in infrared heat, a sign of a surface explosion? Was there an echo in the high-energy crackle of X-rays, evidence of searing temperatures? The answer from every other wavelength was a profound and definitive silence. In the infrared, the Brown Dwarfs continued their steady, cool glow, completely unperturbed. In X-rays, there was nothing, no violent flash to match the radio burst. This multi-wavelength emptiness is what makes the event so deeply anomalous and isolating. A typical stellar flare, even a massive one, is a full-spectrum event. It lights up like a cosmic Christmas tree across multiple bands of light as energy dissipates from the site of the explosion. The Luhman 16 burst did none of that. It was a ghost that only spoke in radio, a scream uttered in a single, narrow language with no accompanying body heat or high-energy fingerprint. This failure to find a counterpart effectively eliminates many of the standard explanations. It was not a simple magnetic flare, as those almost always produce some form of X-ray emission from superheated plasma. It was not an impact event which would have left a temporary glowing hotspot visible in infrared. The burst now stands utterly alone, a one-of-a-kind event with no clear analog in our entire catalogue of stellar behavior. It is a puzzle that grows more profound the more we study it, a solitary data point in the void that challenges our very definitions of what these failed stars are capable of doing. That rhythmic, coded tapping from the vicinity of Teegarden star demanded the most rigorous investigation imaginable. It was a signal that screamed for a deeper look, prompting the world's premier SETI institutes to aim their most sophisticated arrays at that patch of sky. They deployed advanced algorithms designed to sift through the cosmic static, searching not just for repetition, but for the subtle hallmarks of intelligence. These digital detectives looked for mathematical primes, complex error-correcting codes, and other signatures that nature would be hard-pressed to create by accident. For months, the data poured in, a river of numbers scrutinized by both machines and human hope. The sobering conclusion, however, was that the most likely origin remained stubbornly natural. The complex pattern, while mesmerizing, ultimately fit within the known, if poorly understood, spectrum of auroral radio emissions from a brown dwarf's tumultuous magnetic field. It was a lesson in cosmic humility. The universe had presented us with a signal so strange it perfectly mimicked what we thought an artificial message should sound like, only to reveal that nature's palette is far broader and more creative than we had ever assumed. This does not close the case, but rather reframes the entire mystery. If a natural process can produce a signal so convincingly artificial, then how many other potential messages have we dismissed as mere stellar weather? The search continues, but now with a renewed understanding that the greatest challenge may not be hearing a signal, but correctly understanding the voice of the cosmos itself. That slow, drifting sigh from SCR 1845-6357 is more than just a clue, it is a gravitational fingerprint. To decode it, astronomers have turned to the digital universe, constructing intricate simulations that test the limits of the unseen companion theory. They feed variables into powerful computers, asking one fundamental question: could the gravity of a hidden world precisely warp the brown dwarf's motion enough to create that exact, measured frequency drift? The simulations are a cosmic courtroom, and the laws of physics are the judge. The results are both conclusive and astonishing. The answer is a definitive yes. A planetary mass companion with an orbit positioned just right can absolutely impose that gentle, persistent wobble on its parent star. But the implications of this digital proof are what truly reshape our understanding. The simulated object cannot be a massive gas giant like Jupiter. To create the observed drift, the companion must be far smaller, likely a rocky super-Earth or a large icy body. This suggests a planetary system that defies our solar system's template. We are not looking at a failed star with Jupiter-like giants, but perhaps with a family of terrestrial worlds, a stark contrast to our own cosmic neighborhood. The orbital distance derived from the models is equally revealing. The unseen object must orbit quite close to the brown dwarf, completing a full revolution in a matter of Earth years, not centuries. This proximity paints a picture of a compact, tightly wound system, a miniature solar system where a dark, cool star is the sun for a hidden, rocky world. The very existence of such a planet around a brown dwarf carries a profound implication for the abundance of life in the universe. If rocky planets can form around objects that fail to become true stars, then the real estate for potential habitats is far, far greater than we ever dreamed. Every lonely, drifting brown dwarf could be the center of its own hidden planetary system. The drift is no longer just a mystery, it is a map pointing toward a galaxy filled with more hidden worlds than stars. These 25 signals are not merely a collection of isolated curiosities. They form a chorus of contradictions, a unified body of evidence that is actively dismantling our old ideas about these failed stars. Each mysterious transmission is a data point challenging the textbook definition of a brown dwarf as a simple, cooling ember in the dark. The sheer diversity of these emissions, from perfect clocks to chaotic screams, forces a complete re-evaluation of their internal engines. Our models of magnetic activity are proving woefully inadequate. We thought we understood stellar magnetism from studying our Sun and other active stars, but the intense, tangled fields of brown dwarfs operate on a different level entirely. They are not simply weaker versions of stellar dynamos. They are something else, a unique form of magnetic engine that can generate coherent, polarized signals and trigger system-wide energetic duets. The stability of some pulses suggests an order we did not think possible, while the random fury of others reveals a capacity for violence that dwarfs our predictions. This is not just about revising a few equations, it is about accepting that we have been looking at an entirely new class of magnetic object, one whose rules we are only beginning to decipher. The implications ripple outward into atmospheric physics. These signals are our only direct probe into the deep, dark weather systems of these alien worlds. The drifting frequencies and sudden chirps are the sounds of global storms and plasma ejections on a scale that makes Jupiter's great red spot look like a puff of smoke. The chemical anomalies and harmonic chords suggest atmospheric dynamics of breathtaking complexity, where entire global circulation patterns act like a giant musical instrument or a chaotic chemical reactor. We can no longer think of these atmospheres as passive, uniform layers of gas. They are active, seething engines in their own right, capable of generating structured emissions that mimic intelligence and flickering beacons that defy long-term observation. This new, dynamic picture of brown dwarf atmospheres completely reshapes the question of habitability. If these objects can host such powerful and unpredictable magnetic fields and radiation bursts, what does that mean for any potential planets orbiting them? A world huddled close to a brown dwarf for warmth would be subjected to stellar flares of immense power and relentless auroral bombardment. Such an environment might seem utterly hostile, a place where life could never gain a foothold. Yet, the very same signals hint at the existence of those worlds in the first place. The slow Doppler drifts and the fading pulses caused by eclipses strongly suggest that planets, even rocky ones, can and do form around these failed stars. We are faced with a cosmic paradox. The same energetic processes that create these mesmerizing signals might also sterilize the very worlds they reveal. Or perhaps they could provide the energy and the chemical impetus for life in ways we have not yet conceived. The search for these 25 unexplained signals has done more than just catalog anomalies. It has torn open a new frontier in astrophysics, revealing a hidden class of objects that are far more complex, dynamic, and mysterious than we ever imagined. As we stand at the precipice of this new cosmic frontier, the very tools that revealed these mysteries are about to be superseded. The next generation of observatories, now under construction or freshly launched, promises to transform our whispers into conversations. The Square Kilometre Array, or SCAR, will not merely listen to the cosmos. It will hear it with a sensitivity so profound it could detect an airport radar on a planet orbiting a star tens of light years away. When its thousands of antennas across 2 continents finally activate, the SKA will monitor the radio sky with an unblinking eye, catching those fleeting, sporadic bursts that have so far eluded our grasp. It will dissect the harmonic chords and polarized twists with a resolution that could finally distinguish a natural magnetic engine from a designed broadcast. This colossal ear will turn the faint, one-off whispers into robust, verifiable data, giving substance to the ghosts that have haunted our data streams. Meanwhile, soaring a million miles from Earth, the James Webb Space Telescope peers into the infrared soul of these failed stars. Its mission is not to listen, but to see with unparalleled clarity. Webb can directly image the faint, warm glows of potential planets orbiting brown dwarfs, confirming the hidden companions hinted at by those slow, drifting Doppler shifts. It will analyze the chemical chaos in their atmospheres, mapping the global storms and identifying the exotic molecules churned up from the depths. By combining the piercing infrared vision of Webb with the ultra-sensitive radio hearing of the SKA, we will for the first time see and hear these objects simultaneously, creating a holistic portrait of their dynamic lives. Yet, history teaches us that every answered question in astronomy births a dozen new ones. Solving the riddle of one perfect pulse may reveal an even deeper layer of internal complexity we never anticipated. Confirming a hidden, rocky world around a brown dwarf will immediately raise the question of its habitability under such an alien sun. These new instruments will not provide a final answer. Instead, they will hand us a new, far more detailed map of our ignorance, charting territories of cosmic behavior we do not yet have the language to describe. The great symphony from the dark is only just beginning, and we are finally tuning our instruments to hear the full, breathtaking scope of its score. Each of these 25 signals is a single, bewildering piece of a much larger cosmic puzzle. The repeating whisper from the frozen world, the singular scream from Luhman 16, the coded pulses near Teegarden star, they are not isolated anomalies. Together, they form a complex portrait of brown dwarfs as dynamic, chaotic, and deeply mysterious objects. Each signal forces us to add a new, unexpected brushstroke to our understanding, revealing a hidden class of celestial bodies that are far more than simple failed stars. They possess intricate magnetic personalities, storm-racked atmospheres of unimaginable scale, and the potential for hidden planetary systems. This collective evidence is actively rewriting our astronomy textbooks, transforming these dark, drifting worlds from cosmic footnotes into front-page mysteries. Yet, for every question these signals answer, they pose a dozen more. This is the humbling reality of exploring the cosmos. We have built incredible machines to listen to the void, and the void has answered with a chorus of contradictions that defy our current models. The universe is not obliged to be simple, and these 25 unexplained transmissions are a powerful reminder that much of existence remains beyond the edge of our comprehension. The greatest discoveries often begin not with an answer, but with a profound and beautiful question. So keep looking up and keep wondering. If you want to join us as we continue to unravel these cosmic enigmas, subscribe for more journeys into the heart of space's greatest mysteries. And we would love to hear from you. What do you think is the most compelling explanation for these signals? Share your own theories in the comments below. The conversation is just beginning.